All right, this is the video for AP Calculus AB on L'Hopital's rule. So let me preface this by saying if you take AP Calc BC next year, then we will go into all of this L'Hopital's rule stuff again and more. So this is the basics of L'Hopital's rule, which is just the equivalent to exactly what you need to know for the AB exam. There are some other conditions that will need to be looked at for the BC exam, but that's something to worry about another day. So L'Hopital's rule is an approach that we can use when we're doing limits. So yes, we're going to go back to limits today. But it's when situations happen that have happened to you when we were doing limits before, where something that's known as an indeterminate form is achieved. And so what that happens, when that happens, is when f of x and g of x are both 0 at x equals a. So that's one of the situations. So we've done some problems with limits where when we substitute in whatever value it is that x is approaching, we end up with 0 over 0, or even something over 0, 0 being in the denominator. And so the substitution doesn't work for us. In the past, some ways we've dealt with that is by manipulating the f of x over g of x expression using factoring or other things that we know to eventually be able to substitute. But sometimes there is no algebraic way to manipulate. And sometimes even if there is, maybe we don't want to have to go through all that hassle. So that's when you can apply what is known as L'Hopital's rule. But it only works if the limit is initially indeterminate, like something that you could not just straight up substitute and solve. If you can straight up substitute and solve, then don't use L'Hopital's rule. Substitute and solve. So the way L'Hopital's rule works is it actually says that if you have a limit as x goes to a for f of x over g of x, so it does have to be a limit of some sort of fractional expression of one function over another function. The way that we can evaluate that is to find the derivative, notice this, the derivative of f and evaluate it at a divided by the derivative of g evaluated at a. So let me show you an example. We've got the limit as x goes to 0 for sine of x over x. If I was to try to substitute this right off the bat, I would have sine of 0 over 0, and I don't even need to think about the unit circle because I immediately see that I have 0 in the denominator. So this would have been an issue a couple months ago where we would have been stuck at that point. We would have had to try other methods, maybe looking at the graph or using x values that were close to 0 and making a table. But what L'Hopital's rule tells us we can do is take the derivatives of the numerator and the denominator and evaluate their limit. So the derivative of sine of x would be cosine of x, and the derivative of x would be 1. If I evaluate that, I get cosine of 0 over 1. Cosine of 0 is 1. And so the answer for my limit is equal to 1. So let me show you here. Let me pull up my calculator. And if I was to actually go graph, let me see if I can minimize. Move it over. Oh, give me a minute. Let me move it over. Okay. So if I was to graph sine of x over x, I don't need to move it. Okay. So notice that where x is approaching 0, what is the function value close to? Or what is the function value? It is 1. Just like we were able to calculate with our limit there. But prior to now, we would have had to try all sorts of things. And so you're probably frustrated and you're thinking, well, lady, why didn't you teach this to me back when we were doing limits back before? Because I would have aced my limits test the first go round. Yes, you would have if you had known how to do derivatives. But we had to learn how to do all the derivatives of these different functions before we could apply L'Hopital's rule. So that's why we're teaching it to you at this point. So the rest of this video is essentially just going to be us looking at some different problems. So hopefully you'll follow along with me. So the second one here, we've got the limit as x goes to 0 of e to the 2x minus 1 over x. Now, I know in this video all the problems are going to be able to use L'Hopital's rule, but let's say this was my AP exam or my final exam or just some random limits worksheet. I wouldn't know that I could apply L'Hopital's rule until I first tried what I should always try with limits, which is substitution. So you always want to try substituting in, that should be down here, and seeing what happens. So if you do that, then you would immediately see, oh, 0 in the denominator, I've got an issue. So let's try L'Hopital's rule. So we're going to do the derivative of the numerator. Remember, e to the 2x is its own derivative times the derivative of 2x, so that would be times 2. Minus 1, the derivative would just be 0. And then the derivative of x is 1. If I then evaluate that, 2 times 0 is 0. E to the 0 is going to be 1. So I've got 2 times 1 over 1, or my limit answer is 2. Look how easy these limits are. All right, number 3 here. Notice this time we're not doing x going to 0. We're doing x going to infinity. If I was to substitute that in, I would have the natural log of infinity over infinity. Well, then I need to think about natural log of infinity. The natural log graph looks like this. As x goes to infinity, my function continues to rise, and so my y value also goes to infinity. So this would be infinity over infinity. So some of you may want to say, well, that's 1. Anything over itself is always going to be equal to 1. That's not always the case when it's infinities like this. So this is another form of an indeterminate form. Something over 0 is indeterminate, so is infinity over infinity. Now, if it was just the top that was infinity or just the bottom that was infinity, I could evaluate it by substitution. But since they both came out to be infinity, this is an indeterminate form, and so I can apply L'Hopital's rule to it as well. So the derivative of the numerator, natural log of x, is 1 over x, and then the derivative of x is 1. So when I substitute, I get 1 over infinity over 1. Hopefully you remember that 1 over infinity is 0, because the larger the denominator gets, the smaller the fraction value gets. And so our answer, it's not equal to 1 like you may have thought. It's equal to 0. All right, so here we're doing the limit as x goes to negative infinity. If I try to substitute that right off the bat, negative infinity squared is going to be infinity. E to the negative infinity is going to be e to the infinity. Again, the e to the x graph looks like this. So when x goes to infinity, so does the y. So we have another infinity over infinity situation. So again, L'Hopital's rule. Derivative of x squared is 2x. The derivative of e to the negative x is going to be negative e to the negative x. So when we substitute in this time, we get negative 2 infinity over negative e to the infinity, so negative infinity there. Well, that's still got infinities over infinities. You may want to say, oh, but I can cancel the negatives, I can cancel the infinities. The answers are 2. No, when you've got infinities like that, that's still an indeterminate form. So if it's indeterminate after the first go-round, look what we do. We do a second go-round. So now we're going to take this guy and do his derivative. The derivative of 2x is 2, and the derivative of negative e to the negative x is going to be positive e to the negative x. So when I try to substitute into him, I get 2 over e to the positive infinity, which would be infinity. And look at that. My answer is 0. Now, L'Hopital's rule can also be used if you're just doing a one-sided limit, like limit as x approaches from the left or approaches from the right. You don't treat it any differently. You still just use L'Hopital's rule with it. So, for example, here we have sine of x over x again, just like we did back in example 1. But we're approaching 0 from the right. It's irrelevant. I would still get 0 in the denominator if I tried to substitute into this right now. So I can still apply L'Hopital's rule to it because it would be an indeterminate form. So the derivative of sine is cosine, the derivative of x is 1, and so you would get 1 for your answer. Now with number 6 here, we're doing the limit as x goes to infinity of e to the negative x times the square root of x. And so you may be looking at this and going, well, how is that a L'Hopital's rule problem? It's supposed to be a fraction if I can apply L'Hopital's rule to it. And you're right. If I look at it the way it's written right now, that's not a fraction. So then you want to say to yourself, well, is there a way that I could rewrite this as a fraction to where then I could apply L'Hopital's rule to it? So notice how this is a negative exponent. Hopefully you remember the old trick that we can deal with negative exponents by moving the portion that has the negative exponent to the denominator and making it a positive exponent. So then if I was to try to substitute and evaluate that right off the bat, the square root of infinity is still just infinity, and e to the infinity is still just infinity. So again, indeterminate form. So my L'Hopital's rule, if I take the derivative of the square root of x, that's like x to the 1/2. So I've got 1/2 x to the negative 1/2. And the derivative of e to the x is e to the x. Now, if I deal with that x to the negative 1/2 first, this would be like 1 over 2 square root of x over e to the x, or since I've got a fraction over the e to the x, I can write it as 1 over 2 square root of x, e to the x, all in the denominator. Then when you go to substitute, you get 2 times the square root of infinity times e to the infinity, which would be 1 over 2 times infinity, which it doesn't matter how many infinities you multiply together, it's an infinity. And so your answer would be 0. All right, so that concludes the L'Hopital's rule practice. You've got some AP practice questions below there. Give those a try, and we will talk about them the next time I see you in class.